Welcome back, guys. In this part of chapter 14, we're going to talk about the power and efficiency. Why? Because in fact, for mechanical engineering, the power and the efficiency are very strong terms that you're going to use in the future. Now I'm going to start first by the power. What is the power? A power, in fact, is related to the work and it's defined by the work performed per unit of time. So it is as if the rate of the work in time. If a machine or engine performs a certain amount of work du within a given time interval dt, then the power generated by this machine or by this engine will be equal to the derivative of the work with respect to time. So in fact, guys, this power, which is the rate of the work versus time, or which is the work performed per unit time, or which is the derivative of the work with respect to time, is very important, especially if I want to find the output power from a machine or engine. Now, if I want to find the analytical equation of the power, I know in fact that du is the dot product of the force in dr, where dr is the displacement vector. So if I substitute du here by fdr, alright, what I'm gonna have is this equation. So P will be equal to f dr over dt. Now guys, what do you think is dr over dt? This is what? This is the vector v, which means guys, P is the dot product of the force F with the velocity v, which means the power is equal to Fv cosine theta, or it is equal to the force times the projection of the velocity on the line of action. Now guys, I cannot say a negative power unless I mean this is the output power, alright? So this is not the same case of energy or of work. Usually, guys, the work of the force is negative if the displacement projection of this force is in different sign or in different direction of the force itself. Now here, a negative power means that this power is output, or this machine is giving a power. If it is gaining a power, usually by convention, the power is positive. Now, what condition P is equal to 0? P is equal to 0, or there is no power, if the force is perpendicular to the velocity. Because in fact, if the force is perpendicular to the velocity, then the force is perpendicular to the displacement, then there is no work transmitted to this particle, then the energy, the work of the force is equal to 0. So if the work of this force is equal to 0, over the time, the power will be equal to 0. So this power, guys, is a scalar quantity defined as the dot product of the force and velocity, or it is the product of the force and the velocity component acting on the same line of action of this force. So guys, as I said, you can do the dot product equation. P is equal to Fv cosine theta, where theta is the angle between the force and the velocity. And usually, guys, the unit of the power in SI units is joule per second, because it is the energy. And don't forget that the work is an energy, all right? So the energy unit is joule over dt, which is joule per second. Now, if you replace a joule by Newton meter, because I know that the energy, like the work, is equal to the force times displacement, so it is Newton times meter, then you're going to have that 1 watt, which is the unit of the power. So the unit of the power is watt. 1 watt is equal to 1 joule per second, is equal to 1 Newton meter per second. Now, guys, in US unit, I can use the horsepower. Of course, guys, I'm sure guys you heard about this unit, right? So the horsepower is equal to 746 watt, alright? So it is in fact equal to 550 feet pounds per second, which is the US unit, and it's equal to 746 watt if you want to convert it to SI unit. So this is guys for the power. Now what about the efficiency? I'm going to talk about the efficiency because as I said, it's very important, especially in mechanical systems. So in mechanical system, guys, I should measure what is the efficiency of such machine because in fact, what matters for me is to have a machine that has the highest efficiency because in fact, the efficiency is related to the performance of this machine. If there is a lot of friction forces, this means, guys, that I am using energy. The friction force will use the mechanical energy to convert it to thermal energy. So whenever I have a friction, if you do this, guys, if you do this, this is the friction force. You're gonna feel that your hands are hot because in fact this mechanical energy that I am doing using my hand by moving my hands in fact is converted, some of it is converted into heat energy or into thermal energy, and this is also the case of frictional forces. The frictional forces will convert the mechanical energy or the useful energy, some of it, a percentage of this mechanical energy could be converted to thermal energy, and then in this case I am losing this mechanical energy, and this could occur, for example, in your engine, right? So in your car engine, I know that the power is transmitted through gears. So if I have two engaged gears and they are doing a rotation, I could also have some contact, which means I could also have some energy lost, mechanical energy lost. And in this case, guys, the efficiency of my system will not be equal to 1. In fact, for gears, the efficiency is very high and it's about 97%. So what does this number mean? If the efficiency is about 97%, this means, guys, that I have a 3% of lost energy, all right? Because in fact, the efficiency in equation, as you can see here, is equal to the power output from the system to the power input. So I'm giving, guys, my system of gears. I'm taking the example of gears in your engine. I'm giving this gears a certain power input through the shaft that is rotating the gears. Now, what is my power output? If the power output is equal to the power input, this will be the ideal case. So the ideal case is when the efficiency is equal to 1, which means my power output is equal to the power input, or when it is equal to 100%. Now, this is a very rare case because I'm gonna always have some lost energy due to frictional forces or due to wear or due to contact stresses, and in this case some mechanical energy will be converted to some thermal energy. And this means, guys, that my efficiency is always less than or equal to 1. Whenever I have some lost energy, the power output will be less than the power input, and in this case, my efficiency is less than 1. Now, I can also say that the efficiency is equal to the energy output over the energy input because, in fact, I can remove delta T from both sides of this ratio, right? I know that the power is equal to the energy over a certain interval of time, and I know, so I can substitute it in the numerator and denominator and simplify by delta T if I consider the same time interval, and in this case, the efficiency will be equal to energy output over energy input, and don't forget that is less than or equal to 1, the ideal case when it is very close to 1, because I cannot say that the efficiency is 100%. I'm going to have some lost energy. So the ideal case when it is very close to 1. So guys, this is for the power and the efficiency. As I said, they can be used in mechanical system, like for example heat pumps later on your mechanical courses. Thank you.